Okay, you'll see here 1, 2, 3, 4, 5, 6 of the assignment problems. So we're going to go through these one by one. You can look at them one by one. You can look at all of them. You can leave the video behind and come back when you get to a problem, get stuck. So you can use the video as a way to help you do assignment 12. So here are our two equations that we're well familiar with. This is the definition of torque, and it's how we calculate torque. Three things, right? The distance from the force of the axis, the force itself, and the angle, say it, between the R and the F. Be careful about getting the angle right. And so we're going to use that, but the way we're going to solve the problems is these are all static problems, so they're in equilibrium, so it means the sum of the torques have to be 0. So in this case, we're going to get the sum of the torques to 0. And in some cases, we'll use the fact that also, if it's in equilibrium, the sum of the forces in the x direction have to be 0. Whoops. Sum of the forces in the y direction also have to be 0. Why? Because the object isn't accelerated. It's in equilibrium. It's in a balanced condition. So we're going to start this problem with our sum of the torques equal to 0, and we're going to use this to calculate all the torques. Okay, so we write down sum of the torques equals 0, and what this is telling us to do, it's telling us that on the left-hand side of the equation, we're going to add up all the torques, we're going to set them equal to 0, and then we're going to solve for what we want. But when we apply that to this problem, we look at it, we don't necessarily know what the axis is. Is the axis her center of mass? Is the axis the feet? So the first question in the assignment is, what is the reaction force? So if we want to find this force, and we do know her weight because we're given her mass, but we don't know this force, so we're going to set the axis here. Why are we going to set the axis here? Because then this torque will be 0, and if this is our axis, this will be a negative torque, this will be a positive torque, and those two torques will have to be equal and opposite, and we can get the answer we want. So once again, notice what I'm doing. I'm choosing the axis. And you can do this. So I'm going to write it down. The axis that I've chosen are the feet. So I'm going to calculate the torques about the feet. All right. So pause the video and see if you can write down on the left-hand side of the equation all the torques and then set them equal to 0. And then come back and see if what you wrote down is what I wrote down. Okay, do you have this? Now notice I wrote down there were 3 forces. So I wrote down the torque for each force. We don't always have to do that because this torque is 0. Why is it 0? Because the distance, the R, right, the R in the equation is 0. The distance from the axis to the force is 0. This torque is 0. I put a 0 and I wrote it out. Then the next force is negative, so I put a negative sign. The distance is 0.9 meters. I put that in. The force is the weight of the person, which is going to be mg. I didn't put that in yet. And then the positive torque is the 150 times the reaction force that we're trying to find times the sine of 90. Oh, by the way, the weight, notice the person is flat and the force is straight down. So there should be a sine of 90 degrees here as well because the force is perpendicular to the person. Okay, now finish the algebra, put the numbers in, and solve for the reaction force, and see if you can get the answer that I get. Okay, here's the algebra. I crossed this out because it's 0. I crossed the sine 90 out because it's 1. And then I did the algebra. So this is negative, so when I bring it to the other side of the equation it becomes positive, so 0.9 meters times the weight of the person, the mg, 50 kilograms times 9.8 meters per second squared. Notice I wrote all the units. And so then I have to divide both sides by the 150 meters. And notice that the meters will cancel. I didn't cancel them. And so I'll be left with kilogram meters per second squared, which is a Newton. And so the answer that I got, I forgot to write it down, is 294. So 294 newtons. I can cancel the meters. Okay, so now we have the reaction force, and the next question is, what is the FP? And that P, they're using P because that's P for pivot. I would call it F feet. What's the force on the feet? And so for this, it's easier. We don't need to use the torque equation. The easiest thing is to recognize that there are two up forces and one down force. So the two up forces have to be equal to the down force. So to get the FP, use the sum of the forces along y, the sum of the forces in the y direction, equal MAY equals 0. So write that down and see if you can get the answer that I get. Okay, pretty straightforward. Sum of the forces in the y direction equal MAY. In equilibrium, they equal 0. So I wrote down the three forces, two positives, one negative. I did the algebra. Notice the method. And so FP equals the weight minus the reaction force. The weight is mg, 490, minus the 294, and we get 196. Okay, now the second part of the problem is something that we used to do in lab, where we use the same figure. So you go to the lab and you stand on the scale. Let's say this woman was doing it. She would read her mass at 50 kilograms, or if it was a Newton scale, it would read 490 newtons. That would give us her weight. And then she would put her hands, she'd put her feet on the floor and her hands on a bathroom scale, and that would measure the reaction force. And so in this case, we know her weight and we know the reaction force, but what we don't know, you see this 90 centimeters? Notice that we were given that, and 90 centimeters is not half of 150 meters, or her height, which isn't given. So your center of mass isn't necessarily in the middle of your body. You might be top heavy, you might be bottom heavy. So in this case, we're given it, but then in the lab example, we're going to find, so we're looking for this distance. That's what we're trying to find. So use the same equation with the information given, and let's find this distance, the distance from the bottom of your feet to the center of mass. So try that and then come back and see if you did it right. Okay, I think we're done. So here's the equation. Sum of the torques equals 0. Always start with that equation and indicate your axis. I put the feet. And so then I wrote the torques. So I wrote this torque is 0. The next torque is here and it's negative. That's important. And then the last torque is, I called it x hands, the distance from the feet to the hands, times the scale reading, the reaction reading. Now we have a scale, and set all that equal to 0, and then solve it algebraically. So x of the center of mass is going to be x hands times the scale force divided by the weight. I left this in centimeters. There's the scale force it's given. There's the weight it's given. And so we get an XCM of 93.6 centimeters. Oops, I forgot the units. And then it asks to find out the percentage of the total height. You can see that the total height is 180. This is a little bit more than 90. So this person's center of mass is slightly above their midpoint. And so we get a fraction of 0.522, or 52% from the floor to where their center of mass is of their total height. Okay, let's go to the next problem. Okay, I think we can speed up now. So here's the next problem. It's an arm holding a ball, and so you can see the anatomy here. And so there's the person's holding a weight, which is a force down, and there's an elbow joint. So this is a natural axis, right? And also there is a force at this axis, at the elbow joint, that we don't know. That's the E for elbow. So this is what we're going to use for our axis. So when we use our torque equation, we're going to have this be the axis. And so there'll be one force here. And then the thing that causes the arm to lift is this tendon in the bicep muscle. Okay? And in this case, we're ignoring the weight of the arm, which is not really a good idea. In the next problem, we'll account for it. But in this problem, there's just two torques, three forces. Remember, there's a force at the elbow, but the force at the elbow doesn't cause a torque. So write your torque equation and see if you can solve for T. Okay, so you want to practice writing out the equation and doing the general solution, practicing this algebra. So just follow what I did. I set the torques equal to 0. I said the torque's about the elbow, and there's two of them. So this is a number, so I gave it a name. I called it R for the tension force, and I called this R for the weight force, rather than write the numbers in. So the R, the F, and the sine of theta, right? For each one I'm doing an R, an F, and a sine theta, minus the other R, that's the 13 centimeters, times the weight, the 50 pounds, times the sine of that angle. And then I did the algebra, and I got this. This factor goes over there, and then I divide by RT, and I divide by sine of theta t. And so there's the 13 centimeters, there's the 50 pounds. And notice this is a little tricky. The forearm is this way, and the force is down, and so it's the angle between here and there. So there's from here down to here ends up being 120 degrees. Right, it's going to be 60 degrees here plus, wait a minute. Yeah, this is 60 degrees here, right? So the angle between the tension force and the arm is 60 degrees. So that leaves this 30 plus 90. If you bother to do that, that's 120. And so when you do this, you get 433 pounds, or 1927 rounded to 1930 newtons. So it's worth noticing that the tension in the bicep muscle and this tendon is more than 8 times greater than the weight you're lifting. So this is why tendons are subject to very high forces. And why is it? Because the tendon is close to the hinge, the elbow. So the tension force has to be much, much greater than the force that you're lifting. And this is often an issue in sports physiology and physical therapy. So we'll see some more examples of this. Okay, now the last thing is to find the elbow force. And we'll do the same thing we did last time, do some of the forces in the y direction. Okay, so here's the equation. There's the tension force up, the weight down, and the elbow force. And when I solve for the elbow force, I see that it's, I see that it's negative. It's important that it's negative. Yes, the elbow force is down. So the elbow's exerting a force down on the elbow joint, and also a pretty big force. So that's why there's a lot of stress in this joint when you're doing weightlifting. Okay, next problem.